How can we actually take existing optimistic rollups and turn them into zk rollups? Great. So zk rollups are the end game. Why do I say this? Well, zk rollups have a couple of key properties that are uniquely afforded by using them. The first is fast finality. For those of you that have used optimistic rollups before, it takes a week to get your funds off of an optimistic rollup. And this has a lot of bad properties and bad externalities for applications that are building on top of rollups. I've actually talked to a couple of folks that are building applications on rollups, and one of the first questions that gets asked by a user is, if I use your application, do I have to keep my funds in this rollup for a week? And that's one of the main restrictions in them actually adopting that application. So fast finality is something that is quite critical for rollup applications to actually reach scale. Beyond that, zk rollups also afford for interoperability in a way that optimistic rollups don't. One of the key things that has been developing over the past couple months is that there's a lot of optimistic rollups, and people want to move funds from, let's say, OP mainnet to Base, or Base to World Chain. And if you want to do that in an optimistic rollup setting, what ends up happening is you need to execute, or someone needs to execute, every single one of these rollups in parallel. So every single time that you want to, let's say, do a swap or do a transfer from optimistic rollup A to optimistic rollup B, someone is running all of these nodes, and it linearly scales. Every time you add a new optimistic rollup, you now have to run an additional node. With zk, that re-execution does not exist. You simply verify a proof that optimistic rollup B is valid on optimistic rollup A, and you're able to move those assets. So with zk, you actually can reach a scale for interop that doesn't exist for optimistic rollups. Additionally, zk brings great UX for users, and also for developers as well. When you're thinking about reasoning about, optimistic rollup systems, it turns out that the fault-proof mechanism is not only hard to implement, but difficult to reason about. You're essentially playing an on-chain game where, you're bisecting and doing all these, weird terminology to achieve the same property that a zk rollup does, but with finality of a week. And so zk rollups are easier to reason about. They provide fast finality, and they give interop in a way that optimistic rollups simply can't. So I'll talk a little bit more today about how we can actually implement this and why a zkVM is the right approach for zk rollups going forward. So zk rollups exist, right? Like, I'm sure most people in this room have heard of zkSync or Polygon or Scroll, but there's a couple of key issues with these existing zk rollup stacks that makes them not future-proof and difficult to use for rollup teams today. So whenever you look at the code for a zk rollup, what you often find is that all of them are implemented in custom circuits. So you essentially have to take your existing implementation of, let's say, a rollup, which is written in Rust or in Go, as a fork of Geth or Reth, which are the Go Ethereum and Rust Ethereum libraries, and you have to convert it into a custom circuit. The issue with this is that every single time that there's an upgrade to the Go Ethereum library or the Rust Ethereum library, you now have to translate that upgrade. So Ethereum is a hard fork every single year, right? Pectra is the one coming soon. And every single custom circuit team, if they want to maintain compatibility, is going to need to take that Ethereum upgrade and implement it in their custom circuits. So you're redoing work every time there's an upgrade, and you need to maintain cryptographers on your team who understand how to reason about your custom circuit system on board such that they can maintain those upgrades. This results in a lot of potential surface area for vulnerabilities, right? If you have replicated code, you have to audit both pieces of code. So just getting an audit, say, for Geth is not enough. You also need to get your custom circuits audited. And due to the fact that proving was so expensive for the past couple of years, most zk rollup teams made the trade-off of changing how the EVM works. So on zkSync, there's now this zkSync and a couple of other rollups have this terminology of types of EVMs. You have like type 1 EVM, type 2 EVM, and each of these types represents changes to the EVM that are incompatible with the existing EVM or with the EVM implementation that's on mainnet, and it essentially becomes very hard to reason about how you upgrade from a type 4 EVM to a type 1 EVM. And the tooling that a lot of developers use also breaks. You have a custom tooling stack, which isn't really what you want. You don't want to download a new version of Foundry every time you want to make a deployment to, say, a new chain. And kind of the last one I want to touch on is, for a lot of the teams that are deployed today, they're not on zk rollup stacks. Most teams that are deployed with rollups today are built on Optimism or built on Arbitrum, And asking them to move to a new stack is a bad pattern. Really what you want is to bring ZK to where people are rather than asking them to come to you. And with zkVMs, you can actually make this transition possible. You can bring ZK to applications rather than telling applications to learn how to use ZK for them to actually deploy it. Awesome. So what is SP1 and why is SP1 a perfect fit for ZK rollups? So SP1 is our zero knowledge virtual machine. It basically lets you take any Rust or LLVM compilable language, take a program from it, and turn it into a proof, right? So you can take any Rust program, convert it into RISC-V instructions, which can then be proven inside of a zkVM. You could also apply this with, say, Go code or C code. And you can imagine that this lets you take any node software that's used in a rollup and convert it into something that can be proven and verified on-chain. So rather than needing to roll an entire custom circuit stack in order to prove your rollup, you take your rollup software, throw it inside of SP1, prove it, and you're good to go. Now, what this allows is that those entire teams of cryptographers go away. Now, if you're a rollup, all you need is your rollup engineers. Your rollup engineers don't need to think about ZK. They just put what they want to prove in a zkVM that proves it for them, and there's no overhead associated with it. So the overhead for rollup teams goes down for using ZK. Additionally, the upgradability is simple, right? Every time there's an upgrade, you just pull in the latest version of Go Ethereum or Rust Ethereum, and you're good to go. Beyond that, it lets you reuse audits, right? So this problem that I talked about before with every single time you deploy a new upgrade for Ethereum, you now need to get it re-audited. Well, Reth gets audits. Geth gets audits. Now you don't need to re-audit your code anymore. Additionally, I think one of the key points to emphasize is, for a long time, people would ask, well, zkVMs are obviously the ideal approach, right? Like, I don't want to write custom circuits, but it's way too expensive. It turns out that, with rollups and a lot of other real-world workloads, you can do optimizations for specific cryptographic operations that are common. We call this precompiles instead of SP1. So let's say instead of Ethereum, there is ketchaks, which are used to hash together all of the data in Ethereum to get the state root. We can add a cryptographic accelerator for a ketchak. We call this a precompile, and that allows us to match the performance of a custom circuit stack. Additionally, when you have a zkVM, you have more time to optimize the hardware that you're actually using. If you're rolling a custom circuit stack for every single application that you have, you can't go out and optimize that code, right? You need to worry about making sure the application works. You can actually optimize the infrastructure that the application is built on top of. And with SP1, we have the ability to go out and accelerate the hardware. You can imagine this extends beyond just GPUs into FPGAs and ASICs as well. Additionally, with SP1, what I'll show with OP Succinct is that this upgrade path for rollups from optimistic to ZK is now seamless. So let's talk practically about how we can get there. So 2 months ago we launched OP Succinct. It basically lets you take any OP stack chain and convert it into a ZK rollup. Full validity proving for any OP stack chain today. So let's talk about how we can make that happen. Awesome. So I'm going to give a bit of an overview about how optimistic rollups work. This is an architectural diagram of an optimistic rollup. There's 4 main components I want to point out here. There's the batcher, the OP node, the OP geth node, and OP proposer. So basically, what is a rollup? A rollup lets you inherit the security of Ethereum. How does it let you inherit that security? Because you can derive the state of the rollup from the data that's posted to the L1. So your batcher is taking transactions from the L2 and posting it to the L1. Your OP geth node is a fork or a modification of geth that has rollup specific logic. So like, let's say, for example, your rollup supports an additional EIP. You're going to implement that inside of your OP geth node. Your OP node is the consensus, right? So there's a matching consensus layer on the L2 as there is on the L1. And your OP proposer is the one that's proposing the new state roots. So if you want to do withdrawal, you do it against the latest state root that's posted to Ethereum. Now, if you're making a ZK rollup stack, you'd have to roll all of this from scratch, right? You can't just take optimism and plug and play components. But it turns out with the zkVM, it's actually dead simple to substitute one of the components, the only one we need to get full validity proving. So basically what we do is that before we were just submitting the state root. Now, whenever we submit the state root, we also add a proof with it too. So instead of just submitting the state root, we submit the state root and a proof. That proof gets verified on chain. And now you have an immediate finality for withdrawals on the L1 rather than having to wait for a week for that state root to be finalized after the fault proof window is passed. Awesome. OK, so yeah, pretty much it's dead simple. All you have to do is upgrade one contract, and you deploy a service that basically tracks the state of the L2, requests new proofs from the Succinct prover network, and then post those proofs to the L1, and now you have full validity proving on any OP Stack chain. Great. So how do we practically reach a point where you get less than a 1 hour finality? It turns out there's a couple of optimizations and design choices you can make that let you make this happen. So let's say, for example, that you're running a rollup. One thing that's quite important is being able to tune your finality window based on how often you want to post to the L1. You know, if L1 gas prices spike, you don't want to be finalizing every 30 minutes. Maybe you want to finalize every 2 hours. So it's important to decouple the proving of the L2 from the posting to the L1. And so one of the optimizations that we made when we were making OP Succinct is realizing that you can actually prove batches of L2 blocks in parallel. So like, let's say, for example, I want to finalize L2 blocks 0 to 1,000. I can prove L2 blocks 0 to 500 and then 500 to 1,000 separately, put those in two separate sets of GPUs, prove them, and then aggregate them and post them on chain. So we use this layered architecture that gives us the ability to parallelize and also tune the finality window to what the OP Stack rollup wants. So what are the actual costs of this, right? I talked about how zkVMs are now reaching a point where they're competitive with zkVMs. Well, it turns out that the on-chain costs of proposing the new state root are actually quite cheap. Doing a fault dispute game on chain is quite a complex task, whereas verifying a proof is fairly easy to reason about. And so to propose a new state root on chain, it's less than 300K gas, and the proving costs for transactions such as like an ETH transfer or a DEX swap are in the order of either less than 1/10 of a cent or 1/10 of a cent. And we expect that these costs will continue to reduce. We've actually seen an order of magnitude reduction even over the course of the past few months. And when you have a layer like a zkVM, which is consistently going to get better due to better hardware, better algorithmic optimizations, these numbers will continue to get pushed down. Awesome. So one note that I want to make is that one of the other main concerns is there's a lot of heterogeneity in terms of the throughput of rollups. But it turns out that because of the way that zkVMs are designed, you can decouple the restrictions for applications from the proving. And what this means is whether you have an empty chain or you're running Base, which have dramatically different throughput, you can prove either of them with a finality of less than 1 hour because you can infinitely scale the number of GPUs that you have such that you can keep up with any chain. And it turns out that zk workloads are dramatically smaller than traditional GPU workloads, so there's a lot of capacity to scale up into. Awesome. So yeah, as a recap, basically OP Succinct lets you take any OP Stack chain and convert it into a full validity proven chain. It just requires deploying one service and upgrading one contract, and it lets you 100x the finality in your chain. You go from 1 week finality to 1 hour finality, and it shows practically how we can take existing rollups and turn them into the idealized state of what we need for the world computer. Awesome. So yeah, one thing that's also quite nice about OP Succinct is that it's tunable. So as we're in this transitory period where zkVMs are getting adoption, people want to have different security properties. And you can decouple the design of the zkVM from the security properties of your rollup. So your rollup could require having like a multi-proof system where you want like a T plus a zkVM proof. And all of this is completely flexible in the way that the contracts are implemented. Awesome. Yeah, so what does it actually look like today? There's a couple of teams that already have testnets deployed. We expect that a team is going to production with this by mid-November this month, and I think there's a lot of adoption to come. You can see that there's also support for all DA providers, so if you're using an OP Stack chain with Celestia, or you're using one with EigenDA, or even with AvailDA, all of those work with OP Succinct. And so that's been quite cool in that we can support ones that both have Ethereum DA as well as ones that use alternative DA providers. Perfect. And yeah, the project is fully open source. You can see it at Succinct Labs /OP Succinct. It's less than 2,000 lines of code, and it's quite easy to reason about. I don't know if any of you have taken a look at the Optimism fault proof code base. it's kind of crazy to reason about how difficult it is. And here, I think because of how the Optimism team has designed their chain mechanism to be modular, it turns out we can just substitute in OP Succinct without bringing in the mess of the fault proofs. So yeah, awesome. Yeah, and with OP Succinct, we expect that the cost will continue to reduce. We've seen that there are algorithmic optimizations both at the SP1 level, but also within applications themselves. There's going to be a lot of optimizations to be made for how the OP Succinct program that is validity proving the chain can also be updated to be more efficient as well. Awesome. Yeah, so basically, with OP Succinct, we can see a future for what the world computer secured by zk Rollups looks like. It's fast finality. It's applications no longer having to worry about convincing users to move their money onto Rollups because they're afraid of keeping them on Rollups for weeks or for a week. It allows for better interop, right? You no longer have to have a solution for interop that doesn't scale with the number of Rollups. zk interop scales, optimistic interop does not, and it gives you stage 1 for your rollup today. Awesome. Yeah, this has been a lot of fun. If you want to reach out to learn more about OP Succinct or about what we're working on with SP1, feel free to reach out. I've linked my Twitter and my email here. Yeah, this is a lot of fun. Thank you guys.